Just a bit more on the Diels-Alder reaction. Because this involves making a six-membered ring, bringing two things together, it's a very useful reaction. But for that same reason, you're building up, as I said, a lot of complexity. You're building two new sigma bonds. There's stereochemical issues. There's a tendency to be a little bit nervous about it. And I'm hoping to show you that it's really not as bad as all that. The key in thinking about the Diels-Alder reaction is just to remember the key structural pattern of a cyclohexene ring. So in office hours, I started doing this. Here's a flag, and the flag says, "Not in memory of our families and our God and our religion," though all of that is very important, but rather key structural pattern. This is your chemistry title of liberty, and you'll be better at synthesis if you start to recognize these. And the one here for the Diels-Alder reaction is cyclohexene. If you're going to do a Diels-Alder reaction, the product is a cyclohexene. If you had previously done a Diels-Alder reaction and you're looking at the product and trying to think about what the starting materials must have been, the thing you're looking for is a cyclohexene. If you can do that, if you can identify a cyclohexene, a six-membered ring with a double bond in it, the problem is basically over at that point, provided you can count and that you can recognize where the double bond is. So this was the example we did towards the end of class. Here is a six-membered ring Diels-Alder product. You can tell it's a Diels-Alder product because here is the cyclohexene ring. Find the double bond. That's carbons 2 and 3 from your diene. Once you've identified carbons orange 2 and 3 from the diene, then 1 and 4 are clear from that. Then the bonds that 1 and 4 are forming with the other atoms in the six-membered ring, those are the sigma bonds you made in the Diels-Alder reaction. And then the remaining two carbons are purple 1 and 2 from the dienophile. Now, at this stage, if you have copy and paste ability, you can copy the structure. Otherwise, you'll have to redraw it. But you can figure out what the diene would be simply by erasing the bonds between orange 4 and purple 2 and between orange 1 and purple 1. You can also erase the pi bond between 2 and 3. Then you put a pi bond between 3 and 4 and between 1 and 2, and that's your diene. Your dienophile, you're going to need a pi bond here. And this is a dumb way of drawing a pi bond, but remember that the relationship between the groups on the dienophile portion in the ring, if they are trans to each other in the ring, they must also be trans to each other in the alkene, which is why I've drawn the alkene like this over here. Okay? Yes? Right, so what about stereochemistry on carbons 1 and 4 of the diene? In some ways, you've already done that. And I actually will it can get more complicated than I've shown you here. I'm going to stick to what's in the text. Suppose this is your diene. And I'm sorry, off the top of my head, I'm not actually sure what practice exam problem you're talking about. So if you want me to do that one specifically, I'm going to need a little bit of help. Otherwise, if this is fine, then that's fine. Okay, sure. I'm still going to do this. And then maybe we'll do your particular example in a little bit. At this point, yeah, I'm afraid to, no. All right, diene. This is not any different from a regular diene, only carbons 1 and 4 have some other things that they're connected to. Notice that this carbon here is cis to the bond between carbons 2 and 3. This carbon here is cis to the bond between 2 and 3 relative to this pi bond. So there's, even though you're not really thinking about it, there is stereochemistry about these two double bonds. That's of course different in just 1,3-butadiene when both substituents on carbons 1 and 4 are hydrogens. All right, and then I'm not sure what to do. Maybe we'll just keep it simple and we'll let the dienophile be just that. All right, so in the Diels-Alder reaction, we make a 6-membered ring. So 1, 2, 3, 4, 5, 6. There's my cyclohexene product. Just for fun, 1, 2, 3, 4. And carbons 1 and 2. Now, what else am I missing? Carbons 1 and 4 are bonded to other things, right? So, therefore what? So there's a bridge. Okay, and? How should I draw that? Let's start with the hydrogens. And maybe, maybe I'll draw the diene sort of on its edge. Carbons 1, 2, 3, and 4. And then here's the bridge between those two. Here's the hydrogen coming out towards you on carbon 1. Here's the hydrogen going back away from you on carbon 4. And then here is the dienophile. You can use red dotted lines to indicate the new bonds we're going to make. We're going to make a new sigma bond here and another one there. These pi bonds are going to break, and then we're going to make a new pi bond there. Okay, so here is the new 6-membered ring that we're making. So tell me about the, in my new ring, tell me about the relative relationship between the two hydrogens on carbons 1 and 4 respectively. Should they be on the same side of the new ring or on opposite sides of the new ring? Yeah, they're on the same side, okay? It's actually forced to be that way in some ways because of this bridge. This is a 2-carbon bridge. There would be no way for this carbon to be up and that carbon to be down. But the point is, and this is general in Diels-Alder reactions, when you draw the diene in this S-cis conformation, The groups that are pointing outward, in this case these protons, must always be cis to each other in the cyclohexene ring that you make. So we could show that here by showing the protons pointing downward as dashes. And then the two carbons of the bridge, if you want to, we can just put R groups there and call it good. Though, if we wanted to make this a little bit more physically realistic, what we would probably do is that. Sometimes people like to draw this from the side. You can get a little bit better perspective if you draw it from the side. It's not really a chair in the sense that it doesn't adopt the zigzaggy chair conformation. Here's carbons 1, 2, 3, and 4 of the diene. Here's carbons 1 and 2 of the dienophile. Here's the new bonds that we made. And here are those hydrogens that are pointing downward. And here is the two carbon bridge that's sort of pointing upward. So the point, this example illustrates some stereochemical issues on the diene. You can think of the groups on the diene as being two sorts of groups. You have groups that are pointing outward in the S-cis conformation, and then you have groups that are pointing inward in the S-cis conformation of the diene. And the point is that the outward pointing groups must always be cis to each other in the cis to each other across the new cyclohexene ring. That the inward pointing groups, which in this case are covalently attached to each other, also have to be cis to each other, but that the outward and inward groups themselves are going to be trans to each other. Yes?
Would we also get the product where the hydrogens would be wedged and the carbon space in the middle would be dashed, or would that not be a product?
Sure, you're asking, will I also get this product where the hydrogens are a wedge and the bridge is a dash? Yes, that is actually the same product here. And because I've chosen my starting materials carefully, what I just drew here is the pancake flipped version of this. However, you could envision situations where the diene and the dienophile would not be symmetric. In that case, what you're talking about will be the difference between two enantiomers. Yeah. Okay. So this actually complements something that we learned last time about the stereospecificity of the Diels-Alder reaction. We learned, let's see, just want to do this. We learned that there are specific stereochemical requirements for the substituents on the dienophile, that if they are cis in the dienophile, they must be cis in the cyclohexene product. If they are trans in the dienophile, they must be trans in the cyclohexene product. We're seeing some similar stereochemical considerations for the diene. The groups pointing outward must be cis to each other. The groups pointing inward must be cis to each other, but outward and inward must be trans to each other. A related example would just be this. Suppose my diene is this, and my dienophile is this. Here's my Diels-Alder product. Notice that the methyl groups, which were pointing outward when I drew my diene in the S-cis conformation, notice that they are cis to each other in the product and not trans to each other in the product. In contrast, if my diene were like this, then the methyl group there and the methyl group here would have to be trans to each other, right? Because this one is pointing outward, this one is pointing inward. Outward and inward groups in the diene have to be trans to each other in the product. And this is an example of a situation which this molecule is chiral, so we would have also made its enantiomer. I won't draw it, but I'll indicate that it's there with the plus minus. Okay? Now, you'll notice your text very rarely, your text almost never does this. Almost always your diene in the text is either 1,3-butadiene, or it's a diene like this, or like cyclopentadiene, where you can't get confused because there's a covalent linkage between carbons 4 and 1. I'm going to stick to that as closely as I can, but you asked, and therefore I told you. Okay, what else? Yes?
Can we talk a little bit more about exo and endo? Just kind of,
Sure.
yeah, directions there.
Yeah, exo and endo. So I think what you're seeing in the Diels-Alder reaction, based on the examples that I've told you, if you think about that cyclohexene product, there are 4 potential stereocenters that you've got to deal with. I'm running out of colors to describe things differently, so I'm just going to highlight the stereocenters in gray, since that's a fun color. 4 different stereocenters, right? So 2 possible configurations at each stereocenter, 2 times 2 times 2 times 2, 16 potential stereoisomers if you could get all combinations. But what I'm telling you is, because the reaction is stereospecific, a lot of those combinations you don't have to worry about. And so the issue that we have just been talking about groups that are inward versus outward, describes the relative stereochemistry between groups at these 2 carbons, okay? So that's the inward-outward issue. On the diene, on the dienophile, the issue of cis versus trans in the alkene or dienophile and cis versus trans, that's an issue of relative stereochemistry between these 2 carbons. So to sort of summarize, the relationship between groups on these 2 carbons, this is the sort of inward versus outward in the diene, and then cis versus trans in the product. The relationship between these 2 potential stereocenters is cis versus trans in the dienophile, and then cis versus trans in the product. You're going to see that the issue of endo versus exo is going to relate to the relative stereochemistry between the blue and the pink stereocenters. That's easiest to see and easiest to deal with when you do an example like this cyclohexadiene, and then we're going to need a dienophile that has groups on it. We'll only worry about endo versus exo when there is either just one group on the dienophile or perhaps two groups, but they're cis to each other. So let's do this. Here is the diene, here is the dienophile. Just looking through and making some predictions. If you look at the diene, which we've seen before, oops. You have these groups on carbons 1 and 4 that are pointing outward. Those must be cis to each other in the product. You have these groups pointing inward. Those must also be cis to each other in the product. Then on the dienophile, it's a little bit simpler. You just have two carbons, and only one of them has a substituent on it. So there's no stereochemical issues on the dienophile. This ester group isn't cis or trans to anything, it's just protons. When we draw the 6-membered ring product, as we've done before, I will highlight in orange the atoms that come from the diene, in purple the atoms that come from the dienophile. I'm going to choose to draw with the protons down and then the bridge here. All of that has to be that way. There's no choice. The issue of endo versus exo is the substituent on the dienophile, this ester group, is it on the same side as the green substituent from the diene, or is it on the opposite side? Just highlighting stuff again. Maybe it's not useful, and if you hate it, if you hate the colors, that's fine. I've really never had anybody in an end of semester evaluation say that I waste too much time in class coloring. So if you hate it, I encourage you to be the first. So here, the relationship between the blue group and the green group is that they are cis, and therefore this is the exo product. Remember, I told you the endo versus exo was going to be related to relative stereochemical configuration at these stereocenters. If the blue group is trans to the green group, then we call it an endo product. It's thought in general that endo is favored. There are reasons for that your text alludes to. It's sort of not necessary for what we want to do in this class, but that is how you identify the difference between the endo and the exo diastereomers. I will point out that these two Diels-Alder products are chiral. So I will use the plus or minus symbol to indicate that we would get the other enantiomer. So what we're saying here, remember I said, let's see, in this product we make 1, 2, 3 stereocenters, 3 possible configurations, 8 possible isomers. We're getting only 4 of them, and mostly just 2 of them. Okay, you can also think of lots of situations where you can't identify endo versus exo. For example, if this alkene were trans, I can illustrate that simply by copying all of this. And then let's erase that hydrogen and replace it with another ester group. Oops. If I do that, the problem then becomes I still have two different diastereomers, but the problem becomes how do I know, in order to talk about endo versus exo, which is essentially a cis versus trans issue, I have to know which substituent on the dienophile I'm talking about. And when they're identical, how would you even know? So if the substituents on the diene are not cis to each other, you can't really choose endo versus exo anymore. They're still diastereomers, you just can't call one endo versus exo, and if you look at those, there should basically be no difference between having this ester group cis to the green stuff versus this ester group cis to the green stuff. Yes?
So, since we have, this is kind of going back to the orbitals, but we have 4 pi orbitals. Are they just 2 bonding to anti-bonding, or is there a non-bonding?
Oh, sure. So going back to, we've talked about the pi orbitals of the diene and the dienophile. Just looking at the diene, and this describes what's going on in the conjugated system of pi orbitals that's made when you mix 4 p orbitals together. Yeah, the question is, how do I know whether these are bonding versus non-bonding or anti-bonding? And there is an answer to that. I'm not going to ask you about that, but I'll tell you really quickly so you know, but then you can not worry about it or put it in a drawer and come back to it later. Really, to identify bonding versus anti-bonding orbitals, you count up the number of times adjacent atoms have the same wave function sign. And if there's more of those times versus the number of times where adjacent atoms have opposite wave function sign, if there's more same sign adjacent atoms than there are opposite sign adjacent atoms, then it's a bonding orbital. So for example, pi 1, I have 3 times when adjacent atoms have the same wave function sign. In pi 2, I have 2 times where they have a same wave function sign on adjacent atoms, and 1 time when they have opposite sign. You can sort of add and subtract those to tell overall whether it's net bonding or anti-bonding. Both of these orbitals are bonding orbitals, though this is less bonding than that one is. Similarly, if you look at pi 3, I have 1 time where we have the same wave function sign, 2 times where we have opposite wave function sign, so that's an anti-bonding orbital. But it's not quite as anti-bonding as pi 4, where I have 3 times where I have opposite wave function sign. So you can do that in general. That's a good way to rank orbitals. That you don't really need it for what we want to do, in the sense that counting nodes gets you the same relative orientation of the orbitals. But yes, these 2 are bonding orbitals. They are lower in energy than you would expect. And then these 2 are anti-bonding orbitals. The one time you've seen a pi-type non-bonding orbital before has been in the allyl anion or cation, where you had an orbital that looked like this with a node in the middle. Here, there are 0 times where adjacent atoms have the same wave function sign, and there's also 0 times where the adjacent atoms have opposite wave function sign. So that's an example of a non-bonding orbital. All right. So we've dealt with some of the, oh no, I erased some stuff. There we go. We've dealt with some of the stereochemical issues with the Diels-Alder reaction. I still want to practice a little bit the thinking backwards Diels-Alder reaction strategy, and then thinking forwards. Here's one that you are going to hate. Yes?
I just have a question. Does endo and exo only apply if we have a bridge present in the diene?
Does endo versus exo only apply if you have a bridge? In your text, yes. So what if there isn't a bridge? What if you were doing something like this? Could you still assign endo versus exo? Certainly not here because there's no groups on the dieno file. Could you? Yes, it's technically about the relationship between the blue substituents on the diene and the green inwardly pointing substituents, the blue substituents on the dieno file and the green inwardly pointing substituents on the diene. But in your text, the only time they ever ask you to talk about endo versus exo is when there's a bridge carbon. So I'm going to hold to that. Yeah. Okay. The example. You guys really don't want to get to the example you're going to hate, surprisingly. Go ahead.
So if there's two substituents that are different molecules, would that have an effect on which one is the favorite product?
Okay. Maybe. Can you be more specific?
There you have the same molecules, and you said is that maybe.
Oh, so if these two were not identical,
Yes.
would that influence which of these two diastereomers might be preferred?
Yes.
Sure. Since these are diastereomers, one can definitely be preferred over the other. I just don't know I don't know how to predict that. And your question is, if this were something else, could I predict which one of these might be better than the other? Possibly, but I don't know. Possibly, but I don't know how to, I don't know that there's anything easy or useful about that at this stage. Yeah. Okay. The example you're going to hate. So this actually comes from your text. This is problem 12.26. It's a Diels-Alder product that is drawn for you from the side, and it's one that has a bridge, so you kind of have to get used to seeing that. Here's the bridge. You are welcome to bring highlighters into the exam too, by the way, if that helps. It might not, but you're welcome to. Okay, so to some extent, a skill that you're going to gain as you grow in organic chemistry is the ability to focus in on what matters and ignore for the moment what doesn't. It may also help you to gain the skill of redrawing the molecule in a way that's a little bit easier to see. Because I know the answer to this question, I'm going to redraw the molecule in a way that may illustrate things a little bit better, maybe make it worse. Okay. So our task is to think backwards to what the diene and the dienophile might have been. Focus in on the cyclohexene ring. So you're looking for a 6-membered ring with a double bond. Can you see it? And for now, ignore everything that's not that 6-membered ring with the double bond. If you're looking at the structure on the right, that 6-membered ring is here. Nothing else matters. If you're looking at the structure, I said right, but I meant left. Dang it. Here is the 6-membered ring in this view of the molecule. Here is the 6-membered ring in this overhead view of the molecule. Once you've identified that, identify atoms 2 and 3 of the diene. That also gives you 1 and 4 of the diene. 2 and 3 of the original diene are the ones that are involved in the double bond of the 6-membered ring. Atoms 1 and 4 are the diene are the ones that are making the new sigma bonds. And then purple 1 and 2 are from the dienophile. All right, so now draw the diene and the dienophile. Okay, you got it? Okay, so what have you got? The other fun thing about the Diels-Alder reaction is you can always draw that as a starting point for your diene and your dienophile. So, what am I going to put on carbons 1 and 4 of the diene? The diene. A carbon. Come on, help me out. Okay, cyclopentane ring. What else? Need those 2 chloros. All right, good. Got to warm up the crowd a little bit. Any of you, you're probably way too young for this. Any of you watch Elmo's World when you were little? Yeah. Do you remember Mr. Noodle who would always do things wrong? I feel like we're doing that now. So what should my diene be? My dienophile be? No, Mr. Noodle? Right, yeah. Thank you. Okay. You can tell the 2 groups on the dienophile have to be cis to each other because they're cis in the 6-membered ring product. Actually, the dienophile itself is a cyclic product, a 5-membered ring, like that. Okay? All right. Good. Let's do one more. Yes. Yeah. How do I know that one chlorine is up and the other chlorine is down? It's the reason I know that is I guess there's no other choice. On this carbon 5 of the cyclopentadiene, I have 2 chloros attached. I know that carbon's sp3 hybridized, so for shape, one's got to be up and one's got to be down. Yeah. Yes?
So because it's not stereocentric, you don't have to draw.
Because it's not a stereo center, I don't necessarily have to draw it that way. It is totally fine to draw it like this. Understand when you do that, you're not saying that all those atoms are in the same plane of the plane of the page. You are assuming that the reader of your structure understands what an sp3 hybridized carbon is. Yeah. Okay. Yes.
My question doesn't relate to Diels-Alder reactions. I just wanted to ask about what the proton signal was on the practice exam. And
Proton.
like,
Oh, sure. Okay. So there is a question on the practice exam which I should not have put there, and I regretted it, but not enough to take it off, apparently. So sometimes in previous semesters of 351, we don't quite get through with the Diels-Alder reaction before this exam. And so that practice exam question is asking some stuff that you really need to know about something called nuclear magnetic resonance to answer. There is an answer to that. It's not hard, and we'll talk about it in the next couple of weeks before the end. I believe the question was asking for this anion, how many different kinds of carbons and how many different kinds of hydrogens there are. It was asking about things called proton or C13 NMR signals. NMR is an analytical technique that you don't have to know about for this exam, but which allows you to sense different kinds of carbons and different kinds of hydrogens. So if you'll just put that away as context for the question, what we're really asking here is a question about symmetry. How many different kinds of carbons do we have in this molecule? And in order to answer that question, we're really asking about resonance, because as you can see, by resonance, this molecule has some amount of symmetry. If we were to draw the resonance hybrid for this molecule, it would look something like this. There would be partial negative charges on carbons 1, 3, and 5. But you would see that this molecule has mirror symmetry in the sense that carbon 1 and carbon 5 are reflections of each other. Carbon 2 and carbon 4 are reflections of each other. So I would say there's only 3 kinds of carbons in this molecule, because C2 is the same as C4, C1 is the same as C5, and then C3 is its own thing. You could do a similar thing for the hydrogens. The blue hydrogens here, or the orange hydrogens are identical to each other. The blue hydrogens are identical to each other. The yellow hydrogens are identical to each other, and then the pink one is its own thing. That's all this is getting at. Don't worry about the NMR context. The point is that resonance can generate symmetry. Yeah?
Back to the reaction we were doing before. When we form that bridge, and how do we know is there like a mixture of endo and exo products that form?
Right. So here, they're only asking you to think backwards, not forwards. What they've shown you here is the endo product. You can tell it's the endo product because the substituents on the portion that was the diene are trans or opposite the substituent that's the bridge.
I think what I should have asked is like when we're going the opposite way.
Oh, in a predict product sense, would you draw both endo and exo products?
Yeah.
Sure, though you've been taught that the endo is preferred, so the endo product is sufficient. Yeah. Yes? Would we ever have to make a dienophile in like a synthesis problem? This one you wouldn't know how to make. Let me see, a simple alkene, if we were going to make it, a simple alkene you would know how to make. So my answer to that question is going to be annoying, because I'm going to say you won't have to make any dienophiles that you shouldn't know how to make, which tells you nothing. Basically, you know how to make alkenes. So yes, you're responsible for knowing how to make alkenes, but you're not responsible for making the kinds of complicated alkenes that we don't yet know how to make. The examples of things that you should be able to do are in the study guides and the practice exams. Yeah?
For the diamine, where there's green CH3 on the right-hand side, how is that inward?
Sorry, how is that?
Yeah, you said it's like inward.
Right, so here is the diene in the S-cis conformation. I am calling substituents that point this way inward, and I'm calling substituents that point that way outward. Yeah. Yes?
You need to worry about like desaturation levels.
Yes, degrees of unsaturation, which were described in chapter 10. We didn't talk about it at the time. Not for this exam. We will come back to that and use it as a useful way to predict structures of organic molecules. Yeah. Yes?
Would you mind talking about string extension for 1,2-methyl shifts?
I heard the part about 1,2-methyl shifts. I heard the word extension. I have no idea what you mean by that. Could you try again?
Okay, see, I have no idea what it is either. But it got mentioned in a review that a 1,2-methyl shift can like extend a ring. Like,
Oh.
yeah, it can make 500 rings extend.
You're referring to a specific practice problem that looked like this. You have a carbocation, and here is a secondary carbocation adjacent to a quaternary carbon. Now, most of you are probably okay a little bit with the 1,2-methyl shift that moves the methyl group here and puts the positive charge there. Most of you want to scream in horror at what I'm going to show you now, which is, why aren't you screaming? Okay. All that's going on here is instead of the methyl group moving over, there are, notice on this quaternary carbon, there are 3 other carbons attached. Why does it have to be the methyl group to move over? The only difference between a methyl group and this CH2 group is the CH2 group is attached to something else. So if you want, erase all of these and just make these R groups and then redraw it afterwards. But all that's going on, I'm sorry, we have such limited amount of time that I'm going through it pretty quickly. All that's going on here, if I number the atoms 1, 2, 3, 4, and 5, and then call this one 6, all that's going on is carbon 5 is leaning over, breaking its bond with 1, and making a new bond with 6. 1, 2, 3, 4, 5, and 6. So that's called a 1-2 alkyl shift, and it's totally fair and reasonable. It can happen. You just have to not panic and count the atoms. Okay. Good luck.